Section 610, size of potable water piping. So again, we got a .0, beginning of a new section. So this is, do you already know what we're going to learn in this section? We're going to learn how to size potable water pipe. Again, if it's not potable or potable, then the code doesn't care how you do it, right? So this is talking about, these are the proper ways to size potable water piping. Down below there, we got section 610.2, pressure loss. It says where a water filter, water softener, backflow prevention device, tankless water heater, or similar device is installed in a water supply line, the pressure loss through such device shall be included in the pressure loss calculation of the system. All right, so this is number one of five of the worst 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 conditions. The code's going to teach us to size water pipe based under the 5 worst conditions. So the theory is if it'll size water, if our pipe will deliver water adequately of the worst 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 conditions, then it's going to work all the time. So this number one worst here is the worst pressure loss. So if I've got a water filter, water softener, any kind of a backflow prevention device, tankless water heater, anything that's going to rob pressure from that water, then let's take that off right off the top. Now let's look top right there. We got 610.7. These are conditions for using table 610.4. Now let's take a quick look. Jump over to page 111, and this is 610.3, and then on page 112 is 610.4. So on page 112, we've got this table 610.4. So this section we're in says, hey, when you're sizing water pipe based on this, these are the things you need to know. So again, when you look at this table, this is how we're going to size water pipe. While we're here, I want you to notice, do you notice there's 3 different tables here? So the first one there says pressure range 30 to 45 psi, and then down below there, this is the pressure range 46 to 60, and then down below there, hey, if you're over 60 psi, then this is your table, okay? So this is how we're going to size it. So again, we've got your maximum allowable length up at the top. We've got, on the far left-hand side, we've got the meter and street service. That's the size. And then underneath those pressure ranges, that's the WSFU demand, water supply and fixture units. I'll show you that in a minute. All right, let's go back to page 109. It says conditions, top right, page 109, 610.7, conditions for using table 610.4. On proposed water systems, water piping installation size using table 610.4, the following conditions shall be determined. Number 1, I got to know the total number of fixture units as determined from table 610.3, equivalent fixture units for the fixtures to be installed. So what they're doing on 610.3, that is giving us the WSFU demand for each fixture. So if you're a sprinkler guy and you're installing sprinkler heads, you're thinking gallon per minute of flow and then friction per 100 foot of pipe or whatever. So what they've done is they've taken the pressure, the friction loss, and the gallon per minute. They've kind of done a little magic, turned it into a WSFU, water supply fixture unit. So number 1 says I got to take the total number of fixture units as determined from table 610.3. So let's jump over real quick to page 111, and that is table 610.3, page 111. And again, notice the rule, right? Name of the table first, water supply fixture unit, WSFU, and minimum fixture branch pipe sizes. So again, I'm going to learn 2 things in this table. I'm going to learn what my water supply fixture unit value is for this fixture, and I'm also going to learn what my minimum fixture branch pipe size is. So go down your first column, that's your appliance, appurtenance, or fixture. For example, I got a bathtub or a combination bath shower fill. And then the next column, minimum fixture branch pipe size, 1/2 inch. That means to feed that bathtub or combination bath shower fill, we've got to be at least a 1/2 inch pipe going to that. And then next column is private. That's another way to say residential. My house is private, my office is public, right? So private would mean residential, public would mean commercial or industrial. And then assembly, we'd only use the assembly column if we were in some kind of a football stadium or a basketball arena or something like that, right? Where everybody's going to be hitting the water facilities at the same time. So again, according to this table, the bathtub or combination bath shower fill, I need at least a 1/2 inch pipe feeding it. That's the next column. And the demand on that bathtub is 4 WSFUs, right? So again, I'd go to page 112, plug that 4 WSFUs in there. That's what size pipe I would need to feed that. Now again, going back to page 109, 610.7, conditions for using table 610.4. Again, it says, number one, I got to know the total number of fixed units as determined from table 610.3, equivalent fixture units, plural, for fixtures, plural, to be installed. So do you agree the line coming to my house is not just feeding that bathtub or combination bath shower? It's feeding the bathtub and the shower and the toilet and the lav and the sink and the kitchen sink and the, right? So we've got to add all those things together if we're sizing that line feeding the house, right? So everything that's being fed by that piece of pipe, we have to add all those WSFUs together. That would be our total number of fixture units, right? Now, again, if we were to get down that line and there's only 2 fixtures being fed on a piece of pipe feeding these last 2 fixtures on the end, do you agree we'd only take the demand on those 2 fixtures, not the whole thing, right? So whatever's downstream, whatever's still being fed by this water pipe, that's our actual demand on that piece of pipe, right? So we could go from a 2-inch down to an 1.5 inches, down to a 1 inch, down to a 3/4, down to a 1/2 inch, right? Is what they're saying as our demand decreases, WSFU demand. Number 2, I got to know the developed length of the supply pipe from the meter to the most remote. So again, number 1 was the worst fixtures, right? The worst demand of fixtures, assuming, for example, all of them were on at the same time, right? This is the worst WSFU demand we'd ever have. So number 1 on the previous column was the pressure loss through any fixtures or water softeners or water heater, whatever. Number 2, worst, is number 1 here, the total number of fixtures, the worst demand on the water line. Number 2 is your next worst, the worst length of pipe we'll ever have to run. Now notice the code is telling you here, when you size any piece of the water pipe, we're going to use number 2, the developed length. And it says of the supply pipe from the meter to the most remote. So they said from the meter to the furthest run ever in this pipe, that's going to be our developed length, and we're going to use that same number every time. So if my furthest run of pipe from the meter is 250 feet, then we'll size every piece of pipe at 250 feet. That's your third worst, right? Your worst loss, your worst demand at your worst distance. That's 3 of 5 so far. Number 3, difference in elevation between the meter or the other source of supply and the highest fixture or outlet. So again, this is your worst elevation. So from the meter to the highest fixture. Do you agree if my meter is setting here, my highest fixture is up here, I'm going to lose water pressure as I'm pushing that water uphill, right? So the highest fixture, right? That's your 4th worst. Number 4, pressure in the street, main, or the source of supply at the locality where the installation be made. This isn't the worst yet. Number 5 is going to give us the worst in regard to this. But they said, I got to know what the pressure at the main is, right? How much pressure I have sitting there waiting on me. And again, that would be your static pressure with the main closed, right? So I need to know the pressure at the main. And then look at number 5. Here's your next worst. In localities where there's a fluctuation of pressure in the main throughout the day, the water piping system shall be designed on the basis of the worst or minimum pressure available, right? So now we've got the worst friction loss through the fixtures, water softener, whatever. We've got the worst, number 1, we've got the worst number of fixture units. That's assuming those fixtures were all running at the same time. Number 2, we've got the worst length. Number 3, we've got the worst elevation, the worst pressure loss. Number 4 and 5 here, we've got the worst. We've got the worst pressure if there's a fluctuation. Now let's step down below there, 610.8, size of meter building supply piping using table 610.4. We need to pick one more up here. Highlight number 2 for me there, 610.8, number 2. Add or subtract, depending on a positive or negative elevation change, 1/2 psi for each foot of difference in elevation between source of supply and the highest water supply outlet in the building or on the premises. So again, this goes along with number 3 from the 610.7. It says we got to, from the meter to the highest fixture. Now they're saying whatever that distance is, if you're pushing water uphill, we want you to subtract a half a PSI for every vertical foot that you're pushing water uphill, and add a half a PSI for every vertical foot you're dropping water downhill. So what they're going to say is if I push water uphill a foot, I'm going to lose a half a PSI from the meter. If I take water from the meter and drop it a foot, I'm actually going to gain a half a PSI. Okay? Now for years, this was never in the code. They only said subtract a half a PSI from the meter of the highest fixture. They never said add. But now they're saying, you know what, we need to consider that too, because we've already told you your maximum pressure can never exceed 80. That's why they threw this change in there. This showed up about 2003. Okay? So anyways, the worst of the worst of the worst of the worst of the worst. So the worst friction loss through fixtures and fittings, the worst demand, the worst distance, the worst elevation at the worst pressure, right? The 5 worst conditions. And again, the reason the code does this is because do you agree if it'll work under the worst conditions, then it'll work under the best conditions also. If we size a system based on the best conditions, it'll work. And then if we ever had anything less than the best conditions, now the system wouldn't work for us. Okay? Let's move on. So again, let's take a look at section page 110. We've got section 610.10 there. So whenever they rewrote the code here, they moved the tables around. Historically, tables are always at the end of the chapter, which is kind of what they've done now again. But in the last 15, 20 years of codes, they've all been more close to the section numbers. So this will make a little bit less sense to you when we read it. It'll make more sense why we need to know it after we go through it and understand it. So again, first thing I want you to know here, notice here, table 610.10. First, I want you to notice there's 2 tables, right? So remember, the rule is never look at a table till you first read the name. Flushometer fixture units for water sizing using table 610.3. So again, these are flushometer fixture units for water sizing, right? So down below there, notice we got the fixture category water closet with flushometer valves. So this is not the toilet at Wade's house. This is a flushometer valve toilet like the ones we grew up with at school, right? With the one valve on there. Done, right? You can flush that toilet with a flushometer valve and 7 to 10 seconds later you can flush it again, right? We're not waiting for that tank to fill back up so we can flush it. These are flushometer valves. Also know there's a difference between a flushometer valve and a flushometer tank. A flushometer tank is a tank with some kind of a pressure ball in there that puts water in there, pressurizes it, and then forces that water out, right? So this is a flushometer valve. We got a water line coming straight to the toilet. That valve in that line is a flushometer valve. Now, drop down below there a couple of inches. You notice in that horizontal line, again, it says fixture category urinal with flushometer valves. So again, the top half of the table is for flushometer valve toilets. The bottom half of the table is flushometer valve urinals. Okay? Now, when I teach this table, I always like to teach you guys the easiest way to do something. So the easiest way to use this table is to stay out of the middle column. Go from the first column to the third column. And let me show you why. So let's go to the top there where it says water closet with flushometer valves. First column says number of flushometer valves. So let's assume I had 1 flushometer valve water closet. Next column says individual fixture units, right? Assigning decreasing values. So 1 individually would be worth 40 WSFUs, right? And again, notice that is your flushometer fixture units, right? So that'd be 40 fixture units, water supply fixture units. And third column says fixture units assigned for water closet and similar 10-unit fixtures in accumulative values. In other words, this is as I accumulate them. So 1 is worth a total of 40 for a total of 40 because I've only got the 1. 2, the second one, that middle column is saying, hey, the second one's only worth 30 more. But again, you notice if you stay out of that middle column, you go to the first column and the last column, it says 2. By the way, 2 are worth 70. 3 are worth 90. 4 are worth 105. 5 are worth 115. Now be careful with that number 5. 5 are worth 115, period. People say, well, hold on, wait, it says plus 10. Okay, hold on. I've got 5 flushometer valve water closets. That's a total of 115 water supply fixture units. Notice what it says, 115 plus 10. That's where people get in trouble because they partially read and stop and guess what that means. So some people would have said 115 25, 35, 45, 55. That's not true. 115 bought you all 5 of those. 115 plus 10 for each additional fixture in excess of 5. So do you agree if I had 5 flushometer valve water closets, I don't have any in excess of 5, so those 5 are worth 115. What the rest of that means is if I had a 6th one, add 10 more. If I had a 7th one, add 10 more. If I had an 8th one, add 10 more. That's what they're saying. But again, people get in trouble because they partially read this and assume or guess what the rest of it says, and it really gets them in trouble. Okay? So let's move on down below there. Now we got flushometer category urinal flushometer valves. Now, every urinal you've seen in the past 50 years have all been flushometer valves. Right? The only urinal out there that's not a flushometer valve is the one we see in the old gangster movies where the guy's hiding his 1911 up in there, right? And he's got this water tank up there with a pipe coming down with a trough for the urinal, and then he pulls the chain and that water flushes out there to wash out the urinal. Every other urinal you've ever seen with that valve on the side of it, those are all flushometer valve urinals. Okay? So again, stay out of the middle column. First column, number of flushometer valves. Now notice we're halfway through the table, fixture category urinal flushometer valves. So 1 flushometer valve urinal is worth a total of 20. 2 together are worth a total of 35 combined. 3 are worth a total of 45. 4 are worth a total of 53. 5 are worth a total of 58. Right? Period. Plus 5 for each additional fixture in excess of 5. So if I had 5 flushometer valve urinals, are worth 58 WSFUs. This says if I had a 6th one, now it'd be 5 more. If I had a 7th one, it'd be worth 5 more. If I had an 8th one, it'd be worth 5 more. Now also remember per line. So if my water line was feeding 5 of them, my demand would be my demand on the flushometer valve urinals would be 58. By the way, when I got past, if the water line's coming from this direction, when I got past that first urinal, do you agree I'm only feeding these 4 now? Now my demand here would drop down to 53. And when I got past those first 2 and I'm only feeding these last 3 now my demand would be 45, right? How many urinals are being fed by this water line? Okay? A water line might feed all 5 of them, but part of that water line, as you can imagine, as it goes down, is only going to feed that last one. So the water line that's only feeding 1 flushometer valve urinal, first row, 1 flushometer valve urinal will be with a total value of 20 WSFUs. Okay? Now, let's go back to the top of this table. Let's say I have 1 flushometer valve water closet. 1 flushometer valve water closet is worth how many WSFUs? And the answer is 40. Top of the table, fixture category, water closet with flushometer valves, 1, third column, 40 fixture units, right? Now, the reason I want you to see that is let's take a look at page 111. We've got this table 610.3, water supply fixture units, WSFUs and minimum fixture branch pipe sizes. We've already seen this table. I want you to drop down to the very last line there, and the very last line has flushometer valve water closets, right? It says water closet greater than 1.6 gallon flushometer valve. You notice it says see footnote 7. There is no value there. If you go down to the bottom and read footnote 7, it says refer to section 610.10, which takes us right back to this table on page 110. That's a lot of 10s. 610.10 on page 110, right? But it sends us back to this table. It says, hey, if you're a flushometer valve toilet, we're not going to tell you, go back to page 110. If you're a flushometer valve urinal, go back to page 110, right? Section 610.10. So I just wanted you to see that because people say, well, when do I use this table? When do I use the other table? And the answer is always use this table on page 111. What's the name of the table? To determine my water supply fixture units, right? So again, when I go down there and I find a urinal, 1.0 gallon per flush flushometer valve, it says, hey, you got a flushometer valve urinal, see footnote 7. Footnote 7 says go to 610.10, okay? So let's do a quick little sizing exercise here. I'm just going to take the first 5 fixtures off the table. So let's say I got 1 water pipe, that's feeding a bathtub or combination bath shower. It's also feeding a separate 3/4 bathtub fill valve. It's also feeding a separate bidet. It's also feeding a separate clothes washer, and it's also feeding a dental cuspidor sink, right? So let's take all 5 of those, and let's say it's feeding all those. So again, we've got a private, right? So this kind of screwed it up the way they did this in the code. They added that dental unit cuspidor that used to be underneath sink, right? Used to have a dental sink down there. Now they've added it here. So tell you what, let's skip dental. Let's go to dishwasher instead. So bathtub, 3/4 bathtub also, bidet also, clothes washer also, skip the next one, dishwasher, domestic also, right? So we're going to take those 5. So at Wade's house, notice we had to skip that cuspidor because Wade doesn't have a cuspidor sink at his house. So Wade's bathtub or combination bath shower filled privately is worth 4 WSFUs. If Wade has a 3/4 bathtub fill valve for the big garden tub, for example, whatever, that's going to be 10 WSFUs. If Wade has a bidet in his house, that's going to be an additional 1 WSFU. And then if Wade's got a dishwasher, that's funny, they got that backwards. That dishwasher should be the same under private and public. That cuspidor should have been only under public. Funny mistake there in the code. Anyway, that dishwasher is worth 1.5. Sorry, that's what that says. Dishwasher 1.5. Sorry, I got off a line there. So the dishwasher is worth 1.5. So 4 plus 10 is 14, plus 1 is 15, plus 4 is 19, right? So that'd be your clothes washer, and then if I added that dishwasher in there, right, then that'd be 20 and a half, 20.5. 4, 14, 15, 19, 20 and a half, right? So that would be my total demand for all of those if they were in my house. So my demand now is 20.5 WSFUs. So now let's take a look on page 112. On page 112, I'm just going to make this up. Let's say Wade's design pressure, we'll talk about design pressure in a minute. Wade's design pressure is 40 PSI. That's after friction loss, after elevation, the worst pressure, all that. So let's say we're going to run at 40 PSI at Wade's house. So then I'd use the top of that table, 30 to 45 PSI, and I've just got to make up a number. Let's pick a number. The furthest run from the meter, the furthest run in Wade's house is 200 feet, we'll say. Just made that up. We'd go to the 200 column, and now we're looking for 20.5 WSFUs. So going down that 200-foot column, that first line will carry 1 WSFU, next line 5 WSFUs, 13, 15, 21, we're still not there, right? So we had 21.5. So now we step down to 25, that would have to be, now careful here, we got, first column says a 1, second column says 1.25 inches. So we want to stay out of the first column, which is meter and street service, right? That's what the city or the county gives us for water. They give us the street service, they give us the meter. And then the second column, the building supply and branches, that's what we install. So once the city or county sets the meter, then from there, that is our building supply, and then everything within the house is considered a branch. So we're 200 foot looking for 20.5 actually, 20.5. So now we go down 200 foot looking for 20.5, and that's going to take us to 23 at 200 foot. So that's going to have to be 1.25 inches. Okay? So that's 1.25 inches building supply and branches. So again, the building supply is from the meter to the first branch takeoff, and then the building supply is everything else. So 200 foot with a 20.5 at 20 and a half WSFU demand, 1, 6, 15, 17, 23. That's the first one that'll carry that. We go to the left, that would give us 1.25 inches. Now, let's just say, for example, we had a lot of pressure at my house, and my pressure is 80 PSI. Do you agree we do exactly the same thing, except we drop down 46 to 60? No. Down below that, over 60? Yes. That'd be the table I'd use there. Okay? So, again, something you may want to consider is just kind of putting a long, narrow X over that first column, because people have a bad habit of going down and all the way to the left, right? Remember, that first column is if the city were to say, okay, Wade, what size meter do you want? Then I could tell them what size meter I wanted. Now, if you notice, let's take a look at that. Go down that second column, building supply and branches. This is a question that will come up later, so let's address it now. So we've got a 1/2 inch, a 3/4, a 1 inch, and a 1 inch, right? So why do they have a 1 inch building supply and branch on there twice? And if you look to the left, the first one is a 1 inch building supply with a 3/4 meter. The second one is a 1 inch building supply and branch with a 1 inch meter. And then if you look down below there, you got an 1 1/4 inch, 1 1/4, 1 1/4, right? So the difference between those 3 different 1 1/4 building supply and branches is 3 different size meters. Now, again, there's a couple of schools of thought on this. First off, if you're maxing that meter out, you may want to consider a bigger meter. That way, if they ever add a fixture to the house later, there'll still be enough water. But also, we all know that a 3/4 meter is cheaper than a 1 inch meter on a monthly basis because my water bill charges me for meter size and water consumption. So if I've got a 3/4 meter that'll still feed that with a 1 1/4 supply, that would be a cheaper bill for the customer than a 1 inch meter with an 1 1/4 building supply, which is still cheaper than an 1 1/4 meter, still with an 1 1/4 building supply. Okay, so again, I'm just going to reach into thin air, 600 foot, and we'll call it half of that, 300 WSFU demand. 600 foot, 300 demand. So 40 PSI. I just made that up. So 600 foot, 300 WSFUs at 40 foot. So go across the column, 600 foot. Now we go down the 600 foot column. We're on the first table because Wade told us we're at 40 PSI, otherwise we wouldn't know. 600 foot, we're looking for 300 WSFUs, right? That's not even on here. So what that means in a situation like that is we would have to have some kind of special design or engineering done to know what size pipe that needs to be. These tables say you're good up to this. Also notice if our pressure was greater, 46 to 60, you drop down 600. Now we can find our 300 in that 600 column. The last row there is 335 WSFUs. So it would have to be a 2.5 inch building supply and branch. So that tells us two things. We can go without a special engineering standard as long as we're 46 to 60 PSI. So maybe we increase the pressure somehow. Instead of 40, we increase it up to 50. Now we can be in that second table, and I can do a 2.5 inch pipe up to that 300 WSFU demand. Okay? Now, let's walk through this kind of step by step. Okay? So, I've taken those 5 worst to the worst to the worst to the worst to the worst and kind of put them into 3 simple steps here. Step number 1, we got to determine the water supply fixed units per table 610.3, right? So we took the shower fill, the 3/4 bathtub fill valve, the clothes washer, right, the bidet. We added those together, right? That was our total demand. And so that's what number 1 is, right? What all are we feeding on this piece of pipe? Now remember, you determine your fixture demand per pipe based on what's downstream of that pipe. If this pipe is feeding 3 fixtures, you add those 3 fixtures together. If this pipe is only feeding 1 fixture, then that's the only fixture you need to size this pipe to feed. Okay? Number 2, we got to determine the water pressure. And we do that by taking the minimum pressure minus 1/2 of PSI per foot of elevation. Now that's the way I've always taught this, but remember that rule said if you're pushing water uphill, we're going to lose 1/2 of PSI. If you're dropping water downhill, you would actually add 1/2 of PSI. Okay? So that would potentially put you on a different table here, right? So if your meter was at the top of the hill and you're building a house at the bottom of the hill, if we're going to drop 40 foot, we just gained 20 PSI at the bottom of that. Okay? Now also, remember they said add or subtract 1/2 of PSI depending on elevation change to the highest fixture. So I dropped down 40 foot. I got a 20 foot tall house with a shower on the second floor. Then the difference between the meter and the highest fixture in that case will only be 20 foot. Okay? So difference in elevation between the meter and the highest fixture, add 1/2 of PSI if you're going downhill, subtract 1/2 of PSI if you're going uphill for every foot. Number 3, that's going to give you your design pressure, by the way. Number 2, that's going to give us that 35 to 45 PSI, 46 to 60, over 60, whatever. Number 3, use the water supply fixed units. For example, the one we just did, 20.5. The water pressure, right? So the minimum pressure minus half a psi per foot of elevation. And the developed length, again, the distance to the furthest point, that's how we're going to size that. So again, we said 600 foot at 300 WSFU demand, right? We had to step down to that second table to be able to step up to a 2.5 inch building supply and branch to be able to feed that big of a demand at that long of a run. Okay? That's how you would size that. Now there's a couple of, not really tricks, but I put them here as tricks, things you need to know. Number one, hose bibs, right? So let's jump back real quick to page 111, and you've got this table 610.3 here, water supply fixture units, WSFU, minimum fixture branch pipe sizes. Go down that first column, appliance, appurtenance, or fixture, and find me a hose bib. A hose bib is worth 2.5 WSFUs. That means if I've got one hose bib all by itself, it's worth 2.5. Look at the next line below hose bib. It says each additional. So if I've got a water pipe feeding 2 hose bibs, one of them is worth 2.5 and the additional one is worth only 1. If I've got a water pipe feeding 3 hose bibs, one of them is worth 2.5. Do you agree the other 2 are now additional hose bibs? 2.5, 1, and 1, right? So again, one hose bib is always worth 2.5. If you have more than one hose bib, one of them is always worth 2.5 and the additional one's only worth 1. The logic here is I'm probably not going to have all these hose bibs running at the same time. That's the theory. Also, trick number 2 there says flushometer valves per table 610.10. Now again, clearly this is not a trick because if you're paying attention to the table where it says on page 112, where it says see footnote 7, go to 610.10, that refers you to table 610.10. There's no way to find a flushometer valve, water closet, or urinal on that table because it says, hey, we don't know footnote 7. Footnote 7 says, hey, go to 610.10. Section 610.10 says use table 610.10. Number 3 and 4 kind of go hand in hand. Number 3, water heaters only include after the first branch takeoff. Water heaters do not consume water. Water heaters don't drink water. All water heaters do is bring water, store it, heat it, and distribute it out, right? So do you agree? Once that tank and that water heater is full, it'll never consume water ever again, okay? It'll only pass water through there. So number 3 says, only include the water heater after the first branch takeoff. So the first branch takeoff would be the first thing you're feeding on the water line. So from the meter to the house, that's the building supply. The first branch that comes off of that, that's your first branch takeoff. A lot of times the water comes into the house, first fixture it feeds is the water heater. So let's assume the first thing that gets water is the water heater. Well then, between the water heater and the meter, that's your building supply. But once you branch off to feed that water heater, that's your first building supply or your first branch takeoff. In other words, don't include the water heater until after you're past that. After you're past that, then you would include the water heater. And that's when note number 4 comes in, no portion of the piping need exceed the building supply. Now this seems kind of like a contradictory rule. Don't count the water heater till after the first branch takeoff. After the first branch takeoff, count the water heater, but don't make the pipe any bigger. The reason it's not a contradiction is because let's imagine the water heater is at the very end of the water line inside the house. Do you agree that's the last fixture being fed? But let's also assume, just for example, let's assume we're at the laundromat. We're not at your house. We're at the laundromat, and on the very end of the water line, that's where the water heater is. Do you agree? I got to get enough water to the water heater at the very end of the line to produce enough water to turn around and feed all these clothes washers upstream. Does that make sense? So we still got to be sure we're feeding whatever the water heater demand is. And again, there is no demand on a water heater. You calculate the demand on the water heater simply by adding all the fixtures that would demand hot, right? A toilet does not want hot water, so we don't add that. But a lavatory does. Lavatories are worth 1 WSFU. A clothes washer does, right? A kitchen sink does, right? So we would add those fixture units on the lavatory, the clothes washer, and the kitchen sink, and that would be the demand on the water heater. I was going to say actually through the water heater, but that's how you'd size the demand of the water heater. So we have to size this pipe to feed enough water to the water heater to feed whatever may be upstream that needs hot. Okay? Now, careful, because when you're on page 111 and you see that rule about sizing hot water, it says use a half a fixture unit. That's when you're sizing the hot water line only, not sizing pipe for hot water. Okay, so anyway, if you see that note, that's why. So we don't include the water heater till after the first fixture is branched off that water line coming into the building. After that, we include the water heater, but we don't have to make the water heater any bigger than it was coming in. If I was coming in 1.5 inches after the first branch out of the water heater, if it needs to be bigger, I stay 1.5 inches. I don't have to increase it. Because again, we've already calculated the kitchen sink and the clothes washer and the sink and the tub, right? All those things that need hot water. Those have already been calculated, okay? So let's take a quick side note, talk about that. Looking on page 111 here, find me a lavatory. Page 111, table 610.3, first column, lavatory, about 8 or 10 lines down. Notice for a private lavatory, it's worth 1 WSFU. So I just want to clarify for you why we don't include the size of the pipe based on the water heater once we do start counting the water heater. So if I've got a lavatory and I turn all the hot on, I'm going to get 1 WSFU of hot. Turn it off. If I turn the hot off and the cold on a lavatory, I'm going to get 1 WSFU of cold. If I turn on all the hot and all the cold, I'm going to get 1 WSFU of warm. So do you agree that lavatory is never going to demand more than 1 WSFU, whether it's hot, whether it's cold, or whether it's warm? That's why we don't have to increase the building supply line to accommodate the water heater, and why we don't have to increase the branch lines after that to include the water heater, because we've already calculated that lav as 1 hot, 1 cold, 1 warm. It's going to all be the same. Okay? So I just wanted to be clear why we don't include the water heater, why after the first branch takeoff we include the water heater, but we don't have to make the pipe bigger. Okay? Hopefully that makes sense to you. All right, so now let's work through some illustrations and see exactly what we're doing. Now, I want you to pay attention to a couple of these. First off, I call this water sizing diagram number 1, no big deal. But look at your box up there. This is a commercial water supply. Now, do you agree we did not have a commercial column, we had a public column. So this would be the public column. Next line down, 85 foot to the most remote. Do you agree they gave me the developed length right there, okay? So 85 foot, that's going to be the column I'm in. And then the pressure at the main, 70 to 80. Remember what they told us, right? They said, hey, where the pressure varies in the main throughout the day, use the minimum pressure available, right? So in this case, we would base everything based on 70 PSI. We don't care if sometimes it's as good as 80, but the worst it ever gets is 70, right? That's one of our worst. Elevation 16 foot. Now it doesn't say, I'm telling you, we're pushing water 16 foot uphill. We got to know which way we're going. I'm telling you, we're pushing water uphill 16 feet. So do you agree we're going to lose a half a PSI for every foot we push it up? So we pushed it up 16 feet from the meter to the highest fixture. So we're going to lose a half a PSI 16 times. And then the flushometer valve, right? These say flushometer type. These are actually flushometer valve fixture units, right? So the reason the code used to just say flushometer type, and then they added flushometer tank and flushometer valve, so we got to be more specific. So I'm telling you, these are flushometer valve water closets and flushometer valve urinals. So remember, if you're looking at that table on page 111, it's going to say refer to 610.10, right, to get the values for those. All right, so first off, I've got pipe A. A couple of things I need you to know about pipe A is, do you agree this is called the building supply? This pipe A is feeding everything. So remember what they told us, we got to take the total fixed units that possibly may demand on this pipe. So do you agree everything is going to demand water through that pipe A? So I got to feed the hose bib and the kitchen sink and the clothes washer and the lav, and the water closets, 5 of those, flushometer valve, and the flushometer valve urinal, and 3 more lavatories, and an additional hose bib, right? So again, we're going to follow the steps here. So step 1 says we are going to determine the water supply fixed units per table 610.3, right? So what we're going to do is we're going to go to page 111, table 610.3, and we're going to look up our hose bib, right? First thing on the design was a hose bib. 1 hose bib's worth 2.5. So we put that there because that's our first hose bib. And then we go over and drop down, we had that clothes washer and a kitchen sink down there. So clothes washer is worth 4. Kitchen sinks, that's under sink. So that first column down to sink, underneath that kitchen sink is worth 1.5, right? So again, what I would do is in these boxes, I would actually write those values. Hose bib 2.5, clothes washer 4, kitchen sink 1.5, right? So if you have ability to print those pictures out, you can and work on those. And then we would just keep working through. So I'm going to fast forward here. We've got a couple of tricks we've got to pay attention to. When you look at the end of that design, we've got another hose bib down there. So to agree, that's an additional hose bib. So to agree, that hose bib on the end is only going to be worth 1 WSFU, right? Page 111, hose bib 2.5, each additional is 1. So again, you agree they're both being fed by that pipe A. So I've got 2. One of them's worth 2.5, the additional one's worth 1. The second trick they told us to watch out for is these are flushometer valves. But again, when you get to that page 111, you don't get in trouble here, because when you go down there to the water closets and you see that 1.6 gallon flushometer valve, it says see footnote 7, refer to 61010, right? So you can't make that mistake, okay? So when we do that on these flushometer valves, that's going to kick us over to this table, and it's going to say, hey, you have 5 flushometer valve water closets. Remember, stay out of the middle column. First column, go down to 5. Again, we're at the top. Fix your category, water closet with flushometer valves. 5 are worth a total of 115. You can read the note, but you got to read it all every time. 115 plus 10 for each additional fixture in excess of 5. I didn't have any water closets in excess of 5, so those 5 water closets would be worth 115. Again, I would just say water closets 115. Now we also had a flushometer valve urinal, so I'd step down below that, fixture category urinals with flushometer valves. That one flushometer valve urinal is worth 20. So this is what this design should look like. So again, our first hose bibs were 2.5, jump to the end. Your second or additional hose bib was worth 1. Come back to the beginning, near the meter, we drop down. Our kitchen sink was worth 1.5. Our clothes washer's worth 4. Our lavatory's worth 1 apiece. And again, I would just write there 1, 1, 1. Continuing on across, at the end you've got 1, 1, 1 again, right? 3 more lavatories. Going up, we've got those 5 flushometer valve water closets. We found those worth 115. 1 flushometer valve urinal worth 20. Again, 1, 1, 1 on the labs, and then that last hose bib is worth 1 because it's additional on this branch being fed by pipe A, right? Everything is going through A. So add all those together, you get 150 WSFUs, 150 water supply fixed units. So I'm going to put up here on the board real quick the things we're looking for. I've got to know my WSFU demand. So do you agree when I add all those together, I've got 150 WSFUs, right? So, and then I've got to know my design, my developed length, and that is from the meter to the furthest outlet, right? Do you agree that little box there told us we've got 85 feet from the meter to the furthest point, the developed length? Lastly, I've got to know my design, this is an important word, pressure. So my design pressure, to get that, I take the minimum pressure and I'm going to subtract 0.5 PSI per foot of elevation change, right? So in this design, they told us we have an elevation change of 16 feet. So 0.5 times 16, that's going to be 8 PSI. That's how much pressure we're going to lose pushing that water uphill. So if my minimum pressure, according to this design, 70 to 80, my minimum pressure is 70. 70 minus 8 equals 62. That's going to be my design pressure of 62 PSI. Now that I have those 3 things, I'm ready to plug this in to a sizing table. Okay? But the worst of the worst of the worst, and to get this worst, you take this worst and this worst to get this worst, right? So these are 4 of your 5. The only one that's not listed up here is your friction loss or pressure loss through a water softener or tankless water heater or something like that. Okay, that was our first loss. So let's take this information right here. We're going to walk through it as you see it up here on the screen. So again, so far we've got our 150 WSFUs. So let me back up. Step one was to determine our water supply fixed units. So we looked all those up, found them. We total of 150 WSFUs. Now step two is we got to determine the water pressure. And we do that by taking the minimum pressure and subtracting half of PSI per foot of elevation. Now, we're subtracting a half because I told you we were pushing that water 16 feet uphill. Had I not told you, you wouldn't have known whether to add or subtract. Also, if the meter were here and my highest fixture were here, do you agree that's the same elevation, so there would be no difference in elevation. It would just be the minimum pressure. Here we've got a 16-foot elevation. We're pushing it uphill. So a half of PSI 16 times would be an 8 PSI loss. 70 minus 8 would be a 62 design pressure. And then step three, there that is on the screen, 70 PSI minus half of PSI. At 16 foot, be an 8 PSI loss, 62 PSI. And then step three, we use the water supply fixed units of 150, step one. The water pressure, design pressure, step two, 62 PSI. And the total developed length, which they say is from the distance to the most remote point. The table told us 85 feet. Now we take that and plug it into table 610.4, which is on page 112. Now remember, there's three tables here. So look, my design pressure is 62 PSI. First table there at the top, 30 to 45, nope. Down below that, 46 to 60, nope. Down below that, over 60, here we are. Right, so I'm 62 PSI, I'm over 60 PSI. Go back to the top, along that top row, we're looking for 85 feet. Do you agree 85 is not there? So, because 85 is not there, we got to step up to the next one. This is, again, notice the name right above those links, maximum allowable length. So that's a maximum of 80 feet. So if I was running 81 foot, I'd have to step up to 100. Or 90 foot, I'd step up to 100. 101 foot, I would then step up to 150 column. Okay? So it's got to be that number or less. In this case, 80 won't cover 85, so I have to step up to 100. Go down the 100 column to the bottom table. Those numbers in that column at the bottom table are the WSFU demands. So 6 WSFUs, 20, 39, 39, 39. Now notice that's different size meters. 78, 78, 85, and then 151. So my demand is 150. So do you agree that 151 is the first one that will carry it? Now in this case, it's saying you need a minimum of 1.5 inch meter and a minimum of 1.5 inch building supply. But remember what I told you, stay out of that first column. Again, I would just draw a long skinny X and X out that first column. Remember, the top of that first column says meter and street service. That's the street service is upstream of the meter, right? That's the water line in the street. Then they set the meter, and then anything down from that is the building supply, and then everything inside the building is a branch. So do you agree that needs to be 1.5 inches? So pipe A here needs to be 1.5 inches, right? 150 WSFUs, 85 foot at 62 PSI. Okay? Now, let's move on a little bit. Let's take pipe B up here. So if you look at your screen, this is the exact same design, exact same illustration, but do you agree on pipe B, that is going to be to the right of the 3 hose bibs and to the left of the water closet and urinals, right? So what is that pipe in there feeding? Do you agree it's feeding everything downstream? That box on the far left, that's our meter, right? On the other side of A. So everything's coming from the meter down. So I'm not feeding the first hose bib. I'm not feeding those first 3 lavs. I'm not feeding the clothes washer. And I'm not feeding the kitchen sink. So if you remember, those flushometer valve water closets are worth 115. Urinals worth 20. That's 135. Lavs are worth 1 apiece. 135, 36, 37, 38. Careful, because a minute ago that hose bib was 1 because it was an additional. Do you agree it's not an additional now? So now, because it is the only hose bib being fed by that pipe we call B, do you agree that 1 hose bib is now worth 2.5? So 115 plus 20 plus 111 plus 2.5, that would be 140.5 WSFUs. Now we're going to follow the process again, even though we know we're 85 feet and we know we got a 62 design pressure. We're going to work through those steps again because repetition is your best teacher. So again, now my demand up here is the only thing really that's going to change to 140.5 WSFU. So this was pipe A, this is pipe B. So we go down that table. There's not an 85, we go to 100, right? Go down looking for 140.5. That's still going to be 1.5 inches. Now again, do you agree? I'm going to back up a couple of slides. Do you agree? We still had to figure out our design pressure, right? Minimum pressure minus half of PSI. Do you agree the minimum pressure didn't change and the feet of elevation between the meter and the highest fixture still didn't change? So that's not going to change. That means our design pressure is not going to change. And then step 3, we take our design pressure, right, 62, our developed length of 85, and our demand of 140, right, and plug that into the table. And that's where we end up with a 1.5 inches again, right? So that pipe B would still be 1.5 inches. Now look up here. Let's do one more design real quick, and then we'll be done with chapter 6. Remember also, you can rewind this. So if you need to rewind, look at these tables again, especially you test takers, or if you need to rewind and look at the illustrations again, then you can do that, okay? So design number 2, we've got a commercial water supply. So again, we're in the public column, not the private column. 85 foot to the most remote. So I'm going to erase these numbers. It's going to be the same information, and it's going to be the same kind of math, but we don't know what the numbers are going to be yet. So look at that box here on the design number 2, commercial water supply, 85 feet to the most remote. So do you agree we're 85 feet? Right? That didn't change. Pressure at the mains, 70 to 80 psi. We only care about the minimum pressure of 70. Then we're going to subtract a half of psi. The box tells us we've got a 16-foot elevation. Again, we're going to assume we're going uphill 16 feet. Half of psi times 16 feet. Right? That's going to be our 8 psi again. So 70 minus 8 is going to be 62. The reason I'm doing these again is because, again, repetition is the best teacher. It's the same thing we did before. 85 feet, 62 psi. Now, do you agree the demand is going to be different? Because we're not feeding the same fixtures we were feeding before. Now, when I look at this design, I see 2 hose bibs. A hose bib by itself is always worth 2.5. The additional one is worth 1. So do you agree? Call them whatever you want, but those 2 hose bibs are worth 3.5. Right? 2.5 for the first one, 1 for the second one. And then I'll look across there, and I have 1, 2, 3, 4, 5, 6 water closets, and then 3 urinals. Now, people say, well, hold on, Wade. You've got 5 on one branch and 1 on another branch. I agree with that, but what pipe are we sizing? Do you agree pipe A doesn't see those as separate branches? Pipe A, look at me. Pipe A is just looking going, I see 6 water closets out there. I see 3 urinals out there. And I see 2 hose bibs out there, right? It doesn't care how you zig or zag. I'm feeding 6 water closets. I'm feeding 3 urinals. And I'm feeding 2 hose bibs, right? People get themselves in trouble on this design where this design drops to the bottom there and you've got that 1 water closet. They go, oh, that's by itself. It would be if you were sizing that feeder that dropped down that fed the 3 urinals and the water closet. But in this design, we're not, because we're sizing pipe A. It's feeding everything. So step 1, we determine the water supply fixtures per table 610.3. So again, I've only got 3 fixtures on here. I've got 5 flushometer valve water closets, 3 urinals, and 2 hose bibs. So I come here to page 111, table 610.3. Remember the name of the table, water supply fixture units, right? I find my hose bib is worth 2.5. My additional one's worth 1. I'm going to write those values on there. Secondly, I'm going to drop down to my flushometer valve urinal and water closet. Both of those say, see footnote 7, refer to 610.10. That's going to take us over here to page 110. On page 110, I've got 5 flushometer valve water closets there at the top. Fixture category, water closet with flushometer valves, 5, 115. Again, it's okay to read the note, but you got to read it all. 115 plus 10 for each additional fixture in excess of 5. Right? Now I had 6. Do you agree? So those 5 are worth 115. That 6th one is worth 10 more. So again, if it were me, I would just say 125 for water closets and be done. Because when we're sizing that building supply, we don't care where they are. So I've got 6 flushometer valve water closets, right? So I said 5 a minute ago. We got 6. I'll show you the design in a minute. So 115 plus 10 for each additional in excess of 5. I had 5, 115, one more, be 125. Down below that, I have 3 urinals. 3 urinals are worth a total of 45, right? Now, I did something I asked you not to do, and I asked you to stay out of the middle column. The only reason I put individual values in here is to show you how that would work, right? So the first water closet there, high right's worth 40, the second one's worth 30, third one's worth 20, fourth one's worth 15, the fifth one's worth 10. Now, all I need you to see is if you add those together, 40, 70, 90, 105, 115. Do you agree those 5 water closets are worth 115? And then we have one additional down on the bottom, not because it's on a different branch, we just have 6. So here's what that note, plus 10 for each additional fixture in excess of 5. That one flushometer valve water closet there would be worth 10 more. Again, if I were doing this, I would have just said 6 water closets equals 125, been done. 3 urinals equals 45 and been done. So again, this is a little bit more technical than it needs to be. 6 water closets worth 125. 3 urinals are worth 45, done. 2 hose bibs worth 3.5, right? Now we're going to add all those together and we get 173.5 WSFUs, right? 125 plus 45 plus 3.5, right? 173.5. So that's what we're going to put right here. That's our total WSFU demand, right? That's the only thing that changed between these two designs because I kept it at the same developed length and the same minimum pressure, same elevation change, okay? So now, step 2, we determine the pressure. We've already done that. Minimum pressure of 70 minus a half of PSI per foot of elevation equals 16 PSI. So we're going to lose 8 PSI going up. Half of PSI at 16 foot, 8 PSI, be 62 PSI. And then step 3, we're going to take the design pressure, 62, the developed length of 85, and the WSFU demand of 173.5 and plug those in. And now we've got to be a 2-inch. But again, I want you to see where you could get yourself in trouble because some people would answer this 1.5 inches. But do you agree that 1.5 inches all the way to the left is the meter? And that 1.5 inches all the way left is the pipe upstream of the meter called the street service. We do not install those. So after the city or the county sets the meter, I need a 2-inch building supply, right? Now let's look at that illustration one more time. That pipe that drops down, feeding 3 urinals and 1 water closet. If I was just sizing that one pipe, that one vertical pipe that drops down, feeds the 3 urinals and the 1 water closet, do you agree that 3 urinals are still worth 45, just like they were before? But do you agree now, if I was sizing that branch that drops, that water closet now will be worth 40. Is that right? Because back on page 110, they tell me that 1 flushometer valve water closet is worth a total of 40. So if I was sizing just that drop, it would be 40 for the 45 for the 3 urinals plus 40 for the water closet. Make sense? So now just that vertical drop there feeding those 4 fixtures, 3 urinals, 1 water closet, I'd be sizing that at 85 WSFU demand, right? Because we're just, now that branch is only feeding 1 water closet, okay? All right, so that's water sizing. Again, feel free to stop and rewind and rewatch. You can watch this as many times as you need to. If you're confused at all, if you'll just back up and watch this sizing again, it'll pretty much answer any of your questions. Because if you're confused, it's because you missed a piece of this. You got this and this and this, you just missed a piece. So if you watch it again, it'll fill that piece in for you and then it'll make sense to you.